So for this last example, I wanted to do one that had a little bit of a twist to it. So we're asked to consider the region bound by y equals root x and y equals x squared, and we want to find the volume of the solid generated by revolving this region about the y-axis. Now all this, based on what we've done before, the fact that we're rotating around a vertical axis should make you think that we're going to have to do a little bit of maneuvering in this. So we'll kind of see how that plays out in a minute. So let's start with a sketch. So if we were to draw this out, we've got the region bound. So here's our y-axis, here's our x-axis. So we've got y equals the square root of x. So we'll draw that first. So here's y equals the square root of x. And then we'll draw the other curve, y equals x squared. So here's the curve, y equals x squared. So our region of interest here is going to be this enclosed region right here. Okay, now one thing that we have not done yet is we have not drawn our cross section. Now I mentioned this before, but I think it's probably worth explicitly writing it out. So when we are doing a disk or washer method, so for the disk and washer method, the cross section, so cross sections are drawn perpendicular to the axis of rotation. And functions are in terms of the variable of that axis. So in this case, since we are rotating around the y-axis here, I'm going to draw my cross section perpendicular to that axis of rotation. And what defines that location is some value y. That also tells us that our bounds and our functions need to be in terms of y. So our bounds and radii need to be in terms of that variable. In this case, it's going to be y. So one thing that we can note here is we are going to want to put in terms of y in this case. Okay, so let's go ahead and get the bounds and our radii, and then we'll make sure that everything is in terms of y as we need. So for our bounds, as we've done before, we would say let's take our two functions, x squared and the square root of x. We're going to set them equal to each other. And solving this, so maybe we'll square both sides, which would give us x to the fourth is equal to x. And then if we solved this, we would subtract x from both sides, set it equal to 0. We could factor an x out. And this tells us that either x is equal to 0 or x is going to be equal to positive 1. And that kind of makes sense here. So our bounds are going to be from x equals 0 to x equals 1. Now what are our y bounds going to be? Because we need these to be in terms of y. So if x is equal to 0, all we need to do is plug this in to one of our functions. I'm going to pick x squared. So if x is equal to 0, y is going to equal to 0 squared, which is equal to 0. And then if x is equal to 1, then our y bound is going to be equal to 1 squared, or just 1. So we've now confirmed that the bounds along the y-axis are from 0 to 1. All right, so now we've got our y-bounds, and maybe we'll go ahead and make sure we see that specifically. So we're going to go from y equals 0 to y equals 1. All right, so we've got our bounds in terms of y. Now we need to get our radii in terms of y. Now, in order to do that, we're going to have to change our functions. So we've got y is equal to x squared, and we are going to solve for x. And that's going to give us x is equal to, if we take the square root of both sides, we get plus or minus the square root of y. But we know that we're only interested in this first quadrant, so we're going to go with x is equal to just the positive square root of y. And then for our other function, y is equal to the square root of x, we are also going to solve this for x. In this case, we just square both sides, and we get x is equal to y squared. Or let me write this over here, so x is equal to y squared. Now, which one is our outer and which one is our inner? Well, if we go up here and we change these, so this is going to be x equals the square root of y, and this is going to be x equals y squared. The curve that is furthest away from the axis of rotation, the y-axis, is going to be this curve right here. It's furthest away, which is x equals the square root of y. So this is going to end up being our outer radius. So the square root of y, this is going to be our outer radius, big R of y. And then the inner radius, as we talked about, is the boundary curve that is closest to the axis of rotation. In this case, it's x equals y squared. So this would be our inner radius, which we'd call little r of y. So now we've got our inner and our outer radius, and we should be good to set up our volume formula. So let's go ahead and do that next. So volume is going to be equal to the integral from y equals 0 to y equals 1 of pi times the square root of y squared, our outer radius squared, minus our inner radius squared, integrated with respect to y. And since we're going to go ahead and take this all the way through, I'm going to pull the pi outside, still going from y equals 0 to 1. If I square those two individually, I'm just going to get y minus y to the fourth dy. Haven't integrated yet, but if we do that next, we're going to get pi, and that's going to give us 1/2 y squared minus 1/5 y to the power of 5, evaluated from 0 to 1. And that's going to give us, what, 1/2 times 1 squared minus 1/5 times 1 to the 5th. And then we subtracted evaluated at y equals 0, which is going to give us 0. And if we combine these, we're going to get 3/10, which will give us 3 pi over 10. And that would be the volume of this solid. All right, so we've done a number of examples with both the disk and the washer method. We're going to revisit this problem again. There might be an easier way in the next section, but for now we want to make sure that we focus on how we can handle these volumes of revolutions using either the disk or the washer method. So I'd encourage you to go ahead and check out the examples on the worksheet that's posted, and we can move on from there.